I promised that I would give you a quick run through of some of the other methods of data imputation I didn't manage to quite get around to covering in the workshop last week. So I just want to take you back to the data set that we had, and what I've done is I've imputated the sorry, I shouldn't say imputated. I've essentially got to the stage where we removed the data mistakes, and then we also removed the individuals from the data set that had more than 10% of their data missing. So we're back almost to square one really with the data set, just this particular example, and we're at the stage where we have to imputate the data. Now in the lecture we imputated by taking the mean of the nearest point, so it's a kind of a form of regression imputation. But I'm going to show you a couple of additional techniques that have been used by researchers, and these techniques really are different to regression in so much as they attempt to preserve the underlying distributional properties of the variables. So rather than using available data to make estimations, we're really just interested in ensuring that the means, variances and covariances remain the same. So I mentioned in the lecture that one of the ways we can do this is called expectation maximization imputation. And essentially that takes the available information from the data set without missing data, estimates means, variances, covariances, and then uses that as a baseline model to try and imputate values to replicate those means, variances, and covariances. And this is a very simple function in SPSS to do. We just go to our missing value analysis again. What you'll see is that you have a set of variables here. These are all the variables that I have in my data set. We can display variable names to make it easier. But you can see here this is exactly the same data set we worked on in the workshop. And all I'm going to do is pull this across here, like so. So that all the variables that have missing data on them are in the quantitative variable box. Now I'm going to click on expectation maximization, and I'm also going to click on expectation maximization to pull out a sub box or something like this. And what we're telling SPSS to do, if I click this save completed data box, is to produce a separate data file whereby the missing values are imputated using the expectation maximization algorithm. So I'm just gonna call this data set imputated for the moment, and then I'm going to click continue, and then I'm just going to go ahead and click OK, and you'll see here that the expectation maximization function runs exactly as it did for us in the lecture, using exactly the same output. But what's interesting is that not only does it produce the test of whether the data is missing completely random, but it also spits out a new data set, an imputated data set. And you'll notice that in this data set there are no missing values. Okay, so all the variables now are filled in. And that's expectation maximization. It's as simple as that in SPSS. Now you have complete data that you can go and test for outliers, and then you can go and do your inferential statistics. A couple of things to note about this particular form of data imputation. As I mentioned before, because it only runs the imputation process once, we tend to get standard errors that are incorrect, and as a consequence we run the risk of running a type 1 error if we use inferential statistics on this particular data set. But as I mentioned, if you're only doing exploratory analyses, then it's fine to use this particular form of data imputation. So if you do an exploratory factor analysis, whereby you're looking to derive underlying factors from a set of variables without using any inferential test statistics, then this is a perfectly appropriate form of data imputation. So what you then do, of course, is that you'd save your file and then you'd run your subsequent analyses. So that's expectation maximization. That's how it's done in SPSS. Just going to go ahead and remove that val, and I'll also remove the output that we have here, and I'll take us back to the data set that we work from. And I'm going to show you something called multiple imputation. Now, multiple imputation is the preferred form of data imputation when the data is missing when the data is not missing at random. That's to say that there's some systematic reason why the data or why individuals have missed certain data points. Examples I gave, of course, was that if you are younger, you might be less likely to report your income. If you are older, you might be less likely to report your weight. There are reasons that are to do with the characteristics of the data file that mean the data is missing. Now that's missing at random, but it's also used when the data is not missing at random, and that's to say that the reason why the data is missing is for the actual value of the variable itself. So people might not report their weight because they're heavy. They might not report their age because they're older. They might not report their income because it's lower. So the point is that the reason why the data is missing is for the actual variable of interest itself. So under these two conditions, the multiple imputation is the recommended data imputation program. And the reason is because it doesn't just provide one run like expectation maximization. It provides numerous runs, and therefore we can use the standard error that's derived from both within dataset and between dataset runs or imputations. And as a consequence, we have much more reliable standard errors, and we can run inferential statistics even when the data is missing in a systematic way. So again, it's quite straightforward really to run multiple imputation in SPSS because there's a specific function for it. So what we want to do is go down to multiple imputation and just imputate missing data values. Again, all we're going to do is pull over the variables that we're interested in that have missing data on them and pull them across here. Now the default for imputation is 5. Some people say 10, but really once you're past 10, there's no measurable benefit. The estimates don't really become any more robust. So I'm going to leave that 5, but it's up to you how many you want to do. It's based on your own reading of the literature. Exactly the same process for expectation maximization. We're just going to label our new data set that SPSS is going to create for us, whatever we want it to be called. I'm going to call this data set imputation for now. And really, this simple as clicking OK. It will give you some output. It's really irrelevant. What's most important is the data set that is spit out by SPSS as a result of this imputation. Now, what you'll notice in this particular data set is that over here, you'll have a little tool, a drop-down box. And a drop-down box provides each of the runs of imputation and the original data. So here's the original data with the missing values. And then what we have are the subsequent imputation runs. So that's imputation 1, imputation 2, imputation 3, imputation 4, imputation 5. And what you'll notice, guys, is that each individual run spits out slightly different imputated values. So let's take task item 1 for individual 276 here. The imputated value in the first run was 4.29. The imputated value in the second run is 3.39. And of course, it differs again for imputation 3, and again for imputation 4, and again for imputation 5. So what this method does is it takes into consideration the uncertainty that is inherent to imputation at every single run of expectation maximization. So remember, guys, it's slightly more complicated than this, but the basic philosophy of multiple imputation is its expectation maximization imputation, imputation to preserve the underlying characteristics of the data set, but that it takes multiple runs. It gives us multiple estimates based on different iterations of the algorithm. And so what you're left with is an estimate of within data set uncertainty, but also between data set uncertainty, between the runs. As a consequence, you have much more robust standard errors, and therefore we can make much more accurate estimations of whether our inferential statistics are statistically significant. So when there is some reason for the data to be missing, multiple imputation is the preferred approach, and this is how it's done. Now, I would caution that there are problems with this approach in so much as it's an exceptionally burdensome analysis process because you have to run inferential statistics for every single iteration, and then you have to calculate the average estimate and then the standard error based on within and between uncertainty. So it certainly isn't, drawback free, but it's one of the main approaches to handling missing data when it's not missing at random. Okay, so that's multiple imputation expectation maximization. These particular forms of imputation have a number of drawbacks in terms of whether they are overly burdensome or whether they don't produce accurate standard errors. But another drawback of this approach is that when the imputation method is used, and this goes for also nearest point imputation that we did in the lecture, we're taking averages, or we're taking estimates of values that help preserve the underlying characteristics of the data set. And as a consequence, it's often the case that what you'll see is when an imputation method is employed, you'll see something like this, 4.52 or something of this nature. Now, on a Likert scale, participants don't have an opportunity to give an answer of 4.52. It's 1, 2, 3, 4, 5. Now, of course, we're treating these variables as continuous in our analyses. And so for us and anyone who's doing research with Likert scales or quantitative variables that are continuous in their nature, so weight, height, etc., this doesn't matter because the variables are continuous and we take the means and the standard deviations to calculate our variables. But of course, if we're imputating for a yes-no response, then a value of 1.5 is meaningless. You can't be in between yes and no. And so we need a definitive, a determinate response. And so this is why big census data and government department data that you can freely access need determinant points or as imputation points, because otherwise the data won't make any sense. And this is why I wanted to introduce you to hot-deck imputation, because hot-deck imputation is a way that we can use the characteristic data to imputate determinate points for our outcome variables. And I'm just gonna show you how that works now. So this hot-deck is something that's used, as I said, in big data. And when you go to the data cleaning procedures in most of census data, government data, you will find that they will use hot-deck imputation to clean the data set and imputate missing values. Now, I've put a syntax on the workshop materials in Moodle that allows us to employ this imputation method. So what I'm going to do now is just go ahead and I'm going to open, I'm just going to save as, and I'm going to open the syntax. And what you should find is that when you do that in SPSS, you have something that looks like this. Okay, and I'm going to use the original data set again that we've been working through in the workshop. Now what I want you to do is go ahead and just quickly highlight from define all the way up to end define this piece of syntax and run it. Okay, so all that's going to do is load into SPSS the procedure for hot-deck imputation. And then what I'm going to go and do is just provide the subsequent syntax. And I want to show you how this works so that you get a handle on what's going on. Hot-deck imputation is a form of imputation, but for a set of deck variables, that's to say a set of personal characteristic variables, we use to estimate the missing value of an individual on whatever variable that they have missing information for. So, for example, let's say we have missing information for task item 1 here. Okay. And what hot decomputation would do is it would say, okay, well, give me some information about characteristics in your data set. So I can give them information about age, gender, and how many years they've been playing sport. And they can say for that information, what I will do is match participants who are exactly the same across these characteristics, and then take a random individual and use their task 1 item to fill in the missing item for this particular individual. And that's why it's called hot decomputation, because it uses a set of deck variables, those sort of variables that reflect personal characteristics of individuals, to donate their score to the individual missing data. So I'm just going to quickly run this so you get an idea of what's going on here. So I want to imputate task item 1, and I want to use age, gender, and I want to use age, gender, and years playing as personal characteristics to sort our individuals, and then use someone with exactly the same characteristics to make an estimation of what someone would have scored on task 1. And the syntax for that looks exactly like this. Hot dec y, okay, our missing variable value is task 1, / dec, and it specifies our dec variables here that we're going to use to retrieve suitable donors for that missing data point. So again, let's go ahead and run that. And what SPSS will do is it will provide a extra variable here, task 1 hot dec, which is task 1 imputated for the missing values. Now what you'll see is, because we're using donors, okay, because we're using people with exactly the same characteristics, okay, on this particular variable, so age, gender, years playing, SPSS has now used that information and taken the nearest or the closest relation to this individual, borrowed their data point and imputated it. And of course, because the data point has been borrowed, it's imputated at a determinate value. So there's no imputation whereby we have any decimal points here. And that, of course, is a big advantage if this value is a yes-no value or categorical value where there are determinate points. And that's why it's something that's used in census data quite a lot. So if you have data that has categorical variables that need to be imputated, then this is an appropriate technique. It's suggested to be appropriate for low amounts of missing data, even if it's missing systematically. So even if there's some reason why the data is missing, provided there's not much missing, then this is suggested to be an appropriate technique. But as the missing data increases, or the amount of missing data increases, the accuracy of this approach becomes weaker, because it's less likely that there's going to be appropriate matches for each of the data imputation runs. And so as a consequence, it's not recommended when there's large amounts of missing data. But for small amounts of missing data, this is a perfectly acceptable approach, and is an approach that's, as I say, used by government agencies. So, guys, that's the stuff I wanted to cover in this session. If you have any questions, always feel free to give me an email. I'll be more than happy to answer them. And otherwise, I'll see you later this week for a session on regression.